Hey guys, today we are going to be talking about graphs. There's three types of graphs. We're going to talk about two of them today. One is a bar graph. We are not going to be talking about a bar graph today, but a bar graph kind of compares two things on a list, and it shows you visually which one is more than the other. Then we have a pie graph, which is one we're going to be working with today. A pie graph is out of 100%, and it tells you the percentage of people that picked that or voted for that or chose that option. And then we have a line graph, which shows you data over time. So we're going to start with a pie graph. And so if you look at it, this is a national traffic survey. And in a recent survey, asked drivers in several cities across the U.S. if traffic in their area had gotten worse, better, or hadn't changed in the past 5 years or stayed the same. The results of the survey are displayed on the graph. So we got 63% said it was worse, 8% said it was, or 8% said better, 26% said it was the same, and then we had a little sliver right here. And with a pie graph, everything adds up to 100%. So if you take all those and add them together, you get 97, meaning this little chunk right here is 3% of people said that they weren't sure. Okay, that's a good thing to remember. So if we're looking at the questions that go with it, in a town of 4,500 people were surveyed, how many felt traffic improved? Meaning, in a town of 4,500 people, 8% said they got better. So what you're going to do is you're going to take 8% times 4,500 people. Now with percents, remember, you got to put it as a decimal. So you're going to move your decimal point twice. So that'd be 0.08 times 4,500. You take 0.08 times 4,500, you get 360 people said it was better. Okay. In a city of 647,000 people, how many people were expected to think the traffic got worse? So worse, 63% of 647,000 people. So we're going to change this to a decimal. 0.63 times 647,000. And we get 407,610 people said it got worse. And the last one, in a town of 2,500 people, how many people said it was the same? We said same was 26%. So 26% of 2,500. So 0.26 times 2,500 is 650 people. And that's how pie graphs work. You just take the amount of people times the percentage that voted for that, and that tells you how many people are in that group. Education. Estimate the change in enrollment between 1995 and 1999. So in 1995, if you look at this graph, we're at about 14.2 in 1995, I'd say, maybe 14.3. And then in 1999, we're at about 14.9, I would guess. So if you said estimate the change in enrollment between that, how much did it go up? It increased, obviously, so increased. And then how much did it increase? So 14.9 minus 14.2, 0.7. So it increased by 0.7. Okay, on to the next one. If the rate of growth between 1998 and 1999 continued, predict the number of people who would be enrolled in 2005. Predict the number of people who would be enrolled in the year 2005. So let's look at what changed from 99 and 98. So 98, they were at about 0.5, and in 99, they're at about 0.9. So we went from 14.9 from 14.5. So it increased by 0.4 every year, right? So if they're asking if every year it went up 0.4 all the way to 2000, 2001, 2002, 2003, 2004, 2005. They want to know in 2005, if it was 14.9 here, and it's increasing the same every time, what's it going to be in 2005? So we're going to increase by 0.4 every year as an estimate. So this will be 15.3, 15.7, 16.1. I'm just increasing by 0.4 every time. 16.5, 16.9, 17.3. So 17.3 is what I would predict it to be that year. Last thing we're going to talk about with graphs is how they can be misleading. So graphs are very useful for displaying data. However, graphs can be constructed incorrectly and can be confusing and can lead to false assumptions. Many times, these types of graphs are mislabeled, incorrect data is compared, or the graphs are constructed to make one set of data appear greater than another set. What are some common ways? So the first one, a lot of people, they do this, doesn't start a graph at 0. If I don't start a graph at 0, it makes it look much larger than it actually is. Okay, if you think if I started a graph at 0 and I was like, for 10 years I was making $0, but in the 11th year I made $10 and then I made $20, it looks like right away I'm making instant success when I'm not. So starting a graph at 0 is very important unless they label it's not started at 0. Like if they put one of those little graphs and they have the half squiggle in it like that, that's the only way they can't start at 0. But if they don't start at 0, it's misleading. Another way is the labels don't make sense, meaning the question was about money and hours, and the labels say days and chipmunks. I don't know. The labels just don't go together. Okay. The last one is the graph doesn't really connect. I'm going to put graph doesn't connect. And what that means, for a lack of finding a better term, the graph really doesn't correlate with each other, I should say, okay? Meaning I'm measuring how many TVs to how many gallons of orange juice I drank. How many TVs I have to how many gallons of orange juice I drank. My toe size compared to Miss Krigo's car. Those are things that don't connect at all, and then they're going to put them on a graph. So these are the ways that to look out for when they ask you, is this graph misleading? Those are the things to look for. First, does it start at 0? Are the labels right for what they want? And the graph doesn't connect. Okay, hope that makes sense. Thanks, guys.